Check, check. Sorry? I just need another minute to set stuff up. Is that yours? Okay. It's not yours? Just leave it there. Check, check, check. Check, check, check. Check, check, check. Is this loud enough for the people in the back or should it be louder? Is this loud enough for the people in the back? Is this loud enough for the people in the back? Okay.
Hello? 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 I'm Talha. Is that good? Little bit louder. How about now? Like this? Yeah. Okay. Okay.
We'll get started in a minute, so please take your seats so that we can make sure that there are enough seats. If you don't take your seat, you will not be guaranteed a seat because I won't be able to see that there are no seats left over and you standing. So please sit. Stream audio check. Yep.
All right. Hello, everyone. I am Talha. I'm a postdoctoral researcher affiliated with the Ruhr University Bochum in Germany, and I am working remotely out of Trajectory Labs. So today I'll present our work on testing TLS certificate validation using generative language models. So TLS is a fundamental network security protocol. It is used in the vast majority of websites, in mobile applications, as well as IoT devices. TLS is the protocol that ensures your YouTube history remains private from your internet service provider, or that your credit card information gets securely sent to Amazon. An important aspect of TLS protocol is the TLS certificate validation that happens at the start of a connection. For example, here a device is trying to connect to the website, and at the start of this protocol handshake, the server will send a set of certificates called the certificate chain. This step is important because the cryptographic keys that are needed to secure this connection are provided in the certificate of the server. And how can a device ensure that this cryptographic material has not been tampered with or modified by an attacker? There's a signature over this data by another certificate, which is DigiCert in this case. So that sounds straightforward, right? If you receive a certificate chain, you just need to validate the signature and extract the key material. Let's take a closer look at one of these certificates. These certificates are typically encoded in a format called PEM, which is base 64 encoded. And if I decode them, we can notice that there's a lot more complexity to these certificates. For example, there's an expiry date after which this certificate must not be accepted. And as another example, there's this authority field, which specifies how to check if the certificate has been revoked by the signing authority. And if the certificate is revoked, it must also not be validated. Certificate validation is fairly challenging. And to make matters worse, the software that performs certificate validation cannot fail open, meaning it accepts a certificate that should be rejected because that would compromise security. But it can also not fail close because that would lead to denial of service issues. And then, like any other software, the validation software is susceptible to many different programming bugs. And then interestingly, the protocol is defined in these specification documents that are written in plain English. What that implies is that even if the protocol is formally verified, there will still be some room for error. So then what are some of the approaches to test TLS certificate validation? Well, the most obvious thing is to use real-world certificates, and this is indeed the first step in testing software. Unfortunately, real-world certificates lack edge cases that would trigger interesting bugs. So an interesting approach introduced by this work frankencerts mutated pieces of real certificates to come up with a synthetic data set. And this is the seminal work in this area, and the work was very effective in finding new bugs. Unfortunately, the problem with this approach is that most mutations make certificates invalid, and so it's not very efficient. In the work, the authors generated like 8 million certificates to cover different bugs. A more recent approach called Transcert relies on code instrumentation to generate certificates one by one. What that means is that given a certificate, mutations are added on the basis of what improves code coverage. This is the current state of the art in this area. Unfortunately, the issue here is that certificate generation is slow because it relies on code instrumentation, which is getting data about code coverage. But more importantly, because it cannot be trivially parallelized, because each step depends on the step before. In our work, we introduce a simple method, which is to train language models over a data set of real certificates. And once we train these language models, we want to obtain an arbitrary number of test certificates. At a high level, we aim to learn something close to a grammar rather than doing random mutations. And then our approach can also be parallelized by using different GPUs. What is really interesting is that methods that typically rely on language models have to deal with model hallucinations, where models output content that does not align with the goal of the training. But for our case, we are actually interested in model hallucinations because those can trigger interesting edge cases in the libraries that we test. This also means that when we are training language models, our goal is not really to minimize the training loss, but it actually is to improve software testing. So I'll briefly go over the methodology of our work. The first step is to choose the training datasets over which we would train our language models. The insight here is that we need different datasets because the diversity in the datasets influences performance of these language models. For instance, if a version 3 certificate does not appear in a dataset, the model would never learn to output that. So we rely on 3 different TLS datasets for each containing 100,000 certificates crawled online, and you can read the paper for more details. Instead of using the TLS certificates in the compressed notation, we convert them in a textual notation because we understand that language models are really good with exploiting textual data. Fortunately, these certificates are defined in a grammar called ASN, which has an automatic compiler that we can use to convert them from the compressed notation to a textual notation. And then we need to decide which language models to use. While large language models are really popular, it's unfortunately unclear if using those models would help or hurt our task of testing. And the reason it could hurt is that, as I said, if language models can learn a representation of these certificates really well, then they might not trigger edge cases that are more interesting from a software testing perspective. In light of this, we use both RNNs and GPTs. GPTs are more recent, and RNNs have been available for the last 2 decades. And our models vary in the number of parameters that they use, and our results did not indicate using even larger models. We then generate synthetic certificates once our models are reasonably trained. Our training criteria is we stop when the training loss plateaus. We convert these synthetic certificates back into the compressed notation that the TLS libraries expect. And then we test them over multiple TLS libraries through an approach called differential testing to find what we call discrepancies. A discrepancy is when one TLS library differs in its validation outcome from others. Since all these TLS libraries are supposed to follow the same protocol, these cases are interesting because they may highlight the edge cases where some bugs might be. We then analyze our discrepancies using a couple of manual and semi-automated approaches. I'll now talk about some of the results. So first, MLCerts finds more unique discrepancies than previous approaches. Here we visualize discrepancies on the x-axis, and again a reminder, a discrepancy is when one TLS library differs in the outcome. So here metrics SSL says that it's rejected. So because we have 5 TLS libraries, we have 30 discrepancies in total, but on the x-axis here I have 26. First, we just demonstrate that the training data set triggers 4 unique discrepancies, and the heat map talks about the number of certificates that trigger each type of discrepancy, with lighter colors indicating a lot more certificates. And then the benchmarks, frankencerts triggers 2 and transcert triggers 20. And then the 12 models that we have based on 4 datasets and 4 models and 3 datasets, they trigger a wider range of discrepancies. For example, this highlighted region is something that is not covered by the previous models, previous approaches. And then another thing that I would talk about is that even if a discrepancy is covered by the previous approaches, our models find more interesting cases, and that's something that you can read the paper for more details. One last remark I would make is that although there's not a clear winner in our results in terms of which model performs the best, but what is revealing is that some of the smaller models, like this RNN medium, performs as well or better than some of the GPTs. This indicates that maybe large models are not needed for this kind of software testing. Our second result is that model hallucinations, as we predict, indeed help trigger more discrepancies. Here on the x-axis, I play with a variable called temperature that controls the randomness or diversity in language models' outputs. And temperature is a good proxy for generating hallucinated content. First, on the y-axis, I talk about the number of valid certificates. And we can see that as the temperature increases, the number of certificates that are valid go down because the models hallucinate more, which makes the certificates invalid. That is expected. But interestingly, when I plot the unique discrepancies now, we see that a higher temperature actually helps up to a certain extent, after which both discrepancies and certificate validity goes down. So this is interesting because it shows that software testing using language models is not just about training these models on the input data, but it's also about finding the techniques that make these models useful for software testing. And finally, our approach finds some new bugs. I will just highlight one case of interesting bugs where we find that this library GNU-TLS accepts TLS certificates which expire on February 31st, a date that does not exist, but the language models outputted that. And then some libraries allow for leap seconds in time value, which is when the value 60 is added in the seconds field instead of something between 0 and 59. And that is something that is also not allowed by the specification or the grammar. Because TLS has been very widely tested, none of these bugs on our manual analysis lead to software vulnerabilities, but it still demonstrates our approach to find interesting behavior from these libraries. So some of the takeaways are that language models can learn an approximate input grammar suitable for testing. Large language models are not necessarily needed. And then this is not actually the last slide. I have a few more words to talk. I have a few more things to talk about how software testing relates to learning and intelligence in general. So I think we still need to find new techniques that guide these models towards producing diverse test cases. And the reason I say this is because a naive question is, did these models learn how to test TLS software? And my answer is no, these models did not learn any kind of software testing. The only thing they learned was something close to an input grammar. But I learned how to use that input grammar for software testing. So how would it look like if for language models to actually learn to test these certificates? I posit that it's similar to how an intelligent agent would test software, right? If I give you a software and a test case and some test cases and ask you to expand those test cases, you would take a look at the existing test cases, you would make some changes, and then you would observe what happens in the software. And based on those observations, you will continue increasing the expanding the test case. So one model is how it could look like is that if this is our input space, and red or the highlighted dots are the inputs that trigger bugs, and these are the inputs in the training data set, like these are the inputs that are most common in some sense, then the language model would learn a distribution that is obviously biased towards those. But what we would like is for some way to guide the language model to output more interesting test cases. Now, this is interesting because most of the times when LLMs are fine-tuned, we do not want the base representation to be changed significantly. But here our task is very different. Some of the bug triggering inputs might not look anything like a typical TLS certificate, and we need to be able to explore that. But in my opinion, what's even more challenging is that once we have explored this area, then we want to guide the model towards a different region of input space to trigger more interesting bugs. And that's something that's very intuitive for humans. If I demonstrate what a TLS bug is, then you can quickly understand many different examples that trigger the same bug. Like if it's the value 60 in the seconds field, then it does not matter what the hour field is. All those bugs that belong to the same class. But it's fairly hard to understand how we can train the language models to not keep generating the same bugs over and over again. So that's where I would end the talk, that I think at this point, the language models are only learning in my work what a grammar is, but they have no sort of learning associated to how to test these TLS implementations in software well. And I think there's a lot of interesting things that can be explored by more work in this area. That's the end of the talk. Thank you so much.
So we're going to start doing the questions, but please feel free to continue as we go. Anonymous said, could AI possibly generate false codes that trigger dangerous weapons like nuclear, chemical, biological, etc.? And then someone later said in a separate, different thread, I'm assuming replying to this, you can't generate nuke codes from LLMs. Come on. Who do you think, who is right? Can you settle the discussion in here?
I think that's actually a really good point. For me, when I think of existential risk from these really powerful AIs, I am actually worried about cases where the AI could generate code that could trigger the power infrastructure or the hospital industry in a country. When it comes to nukes and stuff, I feel like it's slightly different because, of course, the procedures there are tightened with cryptographic schemes that no one has been able to break because they rely on some mathematical problems from many centuries ago. It's unclear if those problems can be solved trivially. So I think, of course, those kind of things LLMs can't generate. That's the reason LLM can't generate code for accessing the nuclear thing. But what it can do is that it can trigger a bug in the system that handles anything that is powerful infrastructure. And again, I think nukes are mostly not connected digitally. There's some like manual stuff that needs to happen before nukes can be launched. But anything that is digital, these LLMs have the capacity to accidentally find new bugs or weird things.
Giles asks, are there ways to trigger hallucinations other than simply using smaller models?
Maybe I would ask a little bit of clarification about the question, because I think we were generating hallucinations using a higher temperature value, not necessarily through smaller models. Okay, perfect. So the question is what else can we do to trigger hallucinations? So I think we relied in this paper on two things: higher temperature, but also generating a lot of certificates. I let the models run for like a month, and we had like 1 million certificates. So these are two approaches that come to mind quickly, but it's an interesting question because it's possible that different ways of generating the hallucinations can cover different kinds of bugs. Yep.
Owen asks, in the context of TLS certificates, is there a leads towards exploring the input space more intelligently? So what might be a good way to guide the temperature, he asks.
Yeah, that's a really good question. So the current state of the art in software fuzzing in this field is code guided coverage guided input generation, where like you generate an input and you see which lines of the code are triggered, and then you randomly mutate that and you keep doing it over a very long period of time. Like it takes maybe many months and many CPU hours to find interesting bugs. But the problem in that approach is that it's only relying on code coverage, and then it's like people define their own mutation operators and their own strategies that are custom on how to improve the code coverage. And what my argument is that now that we have these language models and machine learning models that capture intelligence in a certain way, maybe we should delegate the task to them how to intelligently explore the input space given the code coverage information. How would that look like? Like, I don't know what strategies would those models uncover, but I feel like the future of software testing would require those kind of black box strategies that these language models would uncover, and not strategies that we have hard-coded ourselves. But in both cases, we would need to rely on code coverage as a reward signal, and then continual learning of some sort. I say continual learning because the software is always evolving, right? And once a bug is found, it's quickly patched. So you're always needing some level of reward signal to guide the model into generating interesting test cases. You can't train a model that generates test cases and call it the best model and call it a day. It does not. Software testing does not work like that.
Anonymous asks, how can you verify if the hallucinated certificates are valid?
That's a good question. So I didn't mention it in the details, but basically every time the model outputs something, it needs to be converted back into PEM notation to be a valid certificate. And many of the certificates fail that filter. But interestingly, we do not want to actually only test valid certificates. It's also important to test some certificates that are invalid, but the libraries might find them to be valid. But we have this filter in our pipeline where anything that is not valid will be like not be able to be converted back into a proper grammar So in some sense, we are actually not just testing TLS software, but we are also testing that compiler, because the first step, like whatever the models generate, the first step is to input that to the compilers. And then when the compilers have made it into a well-formed PEM certificate, then we input that to the library.
Another question from Giles. Can these techniques be expanded to other domains where you might be interested in generating out-of-distribution examples?
Yes, exactly. There's a lot of work right now. It's very popular to ask the language models to generate test cases, because a lot of software relies on like API calls have verbose language that could be first or tested. And I think a few months ago I saw this work where they were using JavaScript fuzzing using language models. So I think software testing in general has this idea that you want to generate out of things that are not from a distribution, but then you also want to test that distribution intelligently. So there's this balance that needs to be handled.
And then Anonymous asks, can you expand more on the impact of this method and the findings? You mentioned something about the bugs being found are not really impacting security. Can you say more?
Yeah, that's a good question. So in my opinion, the impact is quite high because we demonstrate that RNNs work really well for this kind of strategy, and they have been available for the last 2 decades. Now people are more interested in language models because of ChatGPT and using language models for security. But if there is a technique that's been available for last 2 decades and that has not been used, I think that is quite interesting for me. So that's what I think people in the review community of this paper also agreed to, that it shows that we can intelligently generate diverse test cases for testing. In terms of the security impact, again, I did not find any big security vulnerabilities, but TLS is a very critical piece of software. It's been in existence for the last 30 years, so that's kind of expected with this kind of work. But the hope is that this method shows that the test case generation works really well. So even if you have like software with your own grammar, any software that basically parses some input, you can use this kind of method there.
Jack asks, why can't programmatic generation be parallelized? For example, you could just run more instances of the generator program.
Yeah, that's a really good question. So the reason is that, let's say that there's a certificate that needs to be generated that relies on 10 different mutations, but you can only get to the 10th mutation if you have gotten to the 9th and 8th one before it. And let's say that it takes 5 hours to get the first generation, then 50 hours to get the second mutation, and so on. So if you were to generate if you were to run 10 generators in parallel, they would all not be able to reach that certificate with 10 mutations, because those mutations are linked on the prior steps. So that's the answer. I hope it makes sense, but please feel free to come talk to me about it.
And then someone asks, how do you use the test results on the synthetic data sets to tune the model to improve performance?
Yeah, so one approach we are thinking of improving this work is that the test results tell us that, let's say, the 100,000 certificates that the models generated, these 10,000s are interesting, they trigger discrepancies, they trigger some interesting behavior, and the 90,000 do not. So we just use those 10,000 to fine-tune the models further. That is one way, but then I'm thinking that it might not work because the models would just keep generating the same things over and over again. They would find different instances of the same bug. It could be used, but in some sense, do we need that information, or do we need the information of what is not covered, which is what code coverage provides? With code coverage, we can say that, okay, these 100 lines were not triggered by anything in the data set. So maybe the model should have information about the source code and which lines are triggered and which are not triggered to guide the generation.
And then our final question, how might you expand this technique to find vulnerabilities rather than just ambiguously accepted certificates?
So I think that there's a lot of it's an interesting question, and this is what in our paper where we got a lot of pushback as well, that our vulnerability detection technique is quite manual. But software security is quite complex. At this point, we do need experts to combine different bugs to find a vulnerability. A vulnerability is where you're actually able to show that something that is a bug, you can actually use it in a practical way. And these bugs that I talk about, actually they can be used to form vulnerabilities. It's just that in my manual analysis, I was not able to do them. I think there's this new anthropic model that they are saying that is able to find vulnerabilities by tying multiple bugs together. But even that, like, it's not very exhaustive because finding a vulnerability is just, software security is very complex. It is possible that someone can find a vulnerability from something that other people missed for the last 100 years. So basically, it's not a problem with an easy solution. What we can do is try to automate it by learning about how previous vulnerabilities look like what are the class of vulnerabilities. But if there's a new class of vulnerability, how do we automate that?
I know I said one last question, but one just got a bunch of upvotes, so I'm going to ask this question, and maybe this will be the last question for real. Is this complementary to other ML-assisted bug finding? For example, what's going on with Claude Mythos and Glasswing? Could this become obsolete if LLMs just get smart enough?
It's actually not in some sense, because we show, we have this section in our paper that why would we not just ask ChatGPT to generate test cases for us? And the reason is that you need a lot more understanding in the prompt generation then to guide ChatGPT into making interesting certificates. Let's say that there's 100 different features of the grammar, right? You want to ask ChatGPT to make certificates for each feature, but then the LLMs do not have a context window that's that long that they can understand that. And then secondly, more importantly, what I think is the future of software testing looks something like this. This does not mean that those approaches are not going to be useful or impactful. They will be, but software security is always evolving. You can't have an LLM that is smart enough to fix everything, because there will be an LLM that's also smart enough to find new ways to trigger bugs. So as long as this race is going on, and as long as software is evolving, there's going to be new class of bugs. And these current approaches, they are not relying on any sort of this reward signal that I think is very important to intelligently discover new things. And again, some people in machine learning or RL community believe that without a reward signal, there is no learning of some sort. There is no smart enough LLM. You're only smart as if you're always learning.
So thank you so much, Talha. So we will be hanging out for a while. So if you have any more questions, we didn't get to ask all of them. So please do ask him or ask your friends who are here tonight. Make some new friends. Everyone's welcome to hang out until the last Trajectory Labs members leave, which is usually around 9. So yeah, that's all. Thank you.